everyone. Welcome to the Computer Vision Cohere for AI event, in which we are trying to get started with uh, today's exciting guest speaker, uh, Madhuri, and we will discuss about uh, a research paper that's texture matching GANs for CT image enhancement, which uh, she did at Purdue University, if I'm not mistaken.
Right. Yeah.
Yeah, Madurai, please go ahead and take the lead here.
Okay. Um, Thank you, Mayank and Cohere, for inviting me and kind introduction. Um, so today I'll be presenting my PhD research work on texture matching GAN. Currently, I work at Apple as camera algorithms engineer, but this work is not related to my current job. It is part of my PhD. So feel free to interrupt me with questions during the presentation. Let's get started. Um, so the goal of my research was to enhance X-ray CT images. So X-ray CT or computer tomography images are widely used in medical diagnosis. So radiologists or clinical experts can look at these images and do medical diagnosis. So it is very important to have very clean images with good amount of detail. So that is the like ultimate goal of this research. Um, there are different methods to get clean and good images with good detail. So like generally, not generally, the basic principle of CT is like we get these negative log attenuation curves, and then we have reconstruction algorithm to get them in image domain on the as you see on the other two images on the right. So and these images are like consumed by radiologists to do the diagnosis. So one can achieve like the better negative log attenuation by doing improvements in reconstruction domain. But most of the these images are very proprietary to the CT scanners. So academic literature mostly focus on like enhancing image domain reconstructions. And today I worked on both of these aspects, but today I'll present my work in the image domain. So deep learning, it has touched everything. So it also has touched medical CT. It has been around for medical CT for years, as you see on the right graph, but it got like first FDA approval for commercial CT scanner first time in 2019. That was for GE Healthcare, and after that, all medical companies started working on deep learning, and now it's a hot area. But still, while doing deep learning for medical CT, companies have to be really careful because everything goes through FDA approval, and they have to pass like clinical reviews, and it goes through a lot more scrutiny than normal images. So we focused on like how can we get like best quality images from deep learning, and so the core part of this presentation is texture matching GAN, but the building block of texture matching GAN is Bayes-Racine loss function, which I'll present in the first part. So let's start like what is the key problem in current deep neural networks. So these are the noisy input images, which are, you can see these are fairly noisy. And if we apply simple deep neural network, not simple, like even like any advanced deep neural network, it produces like perfectly clean image, which removes everything. And this image looks good to most people, like mainly for engineers. Even to me, I like this image. But if we show this image to radiologists or clinical experts, they don't like this image, and they are the main customer of this technology. So what is the problem with this image is that the texture in this image is getting removed. These results look over smooth to them. So they have been looking at this image for years, and suddenly if we show this image, then it is not going to go through the approvals for clinical reviews. And so for radiologists, texture is very important for the perception. Um, and so G Healthcare actually collected testimonials of multiple radiologists, and they all gave huge importance to the texture. So they like the images on the right side, which has like good amount of texture and good amount of detail. So in medical field or CT imaging, this texture is generally characterized by noise power spectrum. So it is the normalized magnitude square of Fourier transform. So it plots the noise amplitude at increasing spatial frequencies. So let's see the noise power spectrum of these images. So this is the orange curve is the noise power spectrum for this noisy input, and the black line is the noise power spectrum for this result, which is over smooth result. And you can see that this curve is skewed toward the 0 or DC frequency, and higher frequencies are greatly reduced. That is the problem with this image. And what radiologists prefer is to have the noise power spectral shape exactly same as the input, but the noise magnitude reduced. So these plots are normalized. So we just compare the shapes, and the noise magnitude is noted in the noise standard deviation. So ideally, we should have like same noise power spectrum as the input, but the reduced noise amplitude. So all the most of the deep neural networks in literature, they produce as over smooth results, and these are the biased estimator, which wrongly assumes that CT images are highly regularized and they skew noise power spectrum towards 0. So our goal or desired estimator is the estimator with reduced bias and which keeps the noise power spectrum shape intact. And thus we get like texture-rich results. But the challenge is deep neural networks don't have an explicit way to control the bias variance trade-off or noise power spectrum. So we provide methods to achieve these two goals. So let's first see the bias reducing loss function. So the state of the art is convolutional neural network in commercial CT scanners. And the commonly used loss function is mean square error, which has been cited in most papers, and also a lot of papers cite that this mean square error produces over smooth results, and we have seen in our examples too on slides before this. So one method to achieve better texture is the adversarial cost or GANs. They can retain texture, but they could also introduce artifacts or because of hallucinations. And this is medical city, so we cannot have any hallucination or artifacts in images because that could lead to like potential impact on patients. So the fidelity of texture or structural detail is very, very important for reliable diagnosis. So GANs is as it is not a solution for medical city. So we first propose a novel loss function, which we can retain texture and detail. So let's see mean square error first. Like suppose x hat is our estimate and x is the ground truth. Then this is a mathematical definition of mean square error. And if we do if we introduce term this x bar, which is expectation of x hat given x, and if we do mathematical manipulation here, this MSE can be split into two terms, variance and bias. So variance is the noisy variation. By formula, you can see these are the noisy variation because we are subtracting the mean in the estimate. And then bias is the systematic errors remained after averaging. So these are the systematic error which cause like the loss of detail and texture, and these errors uh, cannot be removed even after averaging. So, so these are the bias types of errors we want to reduce. But mean square error gives like equal weightage to bias and variance. So we propose a new error metric. So let's see this bias variance trade-off curves. So this is a conceptual representation, which is the core of every machine learning problem. This curve basically says that we cannot reduce bias and variance at the same time. So if we train our network with mean square error, then we are giving equal weight to the bias and variance. Then solution lies at the intersection of this curve and the equal intercept line. This solution is over smooth. That means it has higher bias than we desire. So our solution should have less bias and we can tolerate a little bit higher variance. That's our desired solution. And to achieve that solution, we propose to reduce the weight of the variance term in the training so that relative importance or relative weight of the bias term would be increased and network would be penalizing bias more in the training. And as a result, in inference, we get more textured solution with higher variance and less bias. So this is our bias weighted MSE where we weight variance term by lambda and lambda is less than 1. Now, question is, how do we realize this bias weighted MSE in a neural network or with a loss function? So this is our network which realizes this metric. So we start with the ground truth image X, and then we add two independent noise samples to the same ground truth image xk, and then we get two noisy input images yk1 and yk2, and then we pass them through our denoising network. Note that I have shown like two boxes, but these networks, these two boxes share the same parameters. So these are like Siamese network. And then once we get so we pass our input images to this network, and then we get the two estimates. And then we we compute the weighted average of these two estimates to get Z at K1. And we use this Z at K1 to compute the loss mean square error with respect to true ground truth image XK. And then gradient would be back propagated to the network to update the weights. So this is our loss function term. And so this assembly achieves the target of reducing the weight of the variance term. And in our paper, like we proved that this loss function approximates bias weighted MSE for lambda equal to alpha square plus 1 minus alpha square. And once we have one pair of this weighted average, we can easily switch the weights to get an extra sample for training, and that's our Z hat K2. So our total loss function is just addition of these two mean square errors, and then we average over all the training samples. So this is our core architecture. Let me show you some results. This is our experimental setup. For clean images, we use clinical images, and then noise. If you recall from the first examples I've shown, the most of the noise part, it comes from muscles, and muscles are mostly made up of water. So in CT imaging, noise, water phantom scans are generally representative of noise. So we take noise samples from water phantoms, and then we add them to get noisy images. And for testing also, we have clinical images for testing. Let's first see how alpha or lambda values affect the results. So to recall, like if lambda is 1, this is same as mean square error, and as lambda reduces, the variance weight reduces, and then we should get more and more bias reduction. So these are the results with alpha, and this curve is symmetric. So results from alpha 0 to 0.5 and 0.5 to 1, they should produce the similar results. So when alpha is 1, lambda is 1, and then we get results with results same as MS, mean square error. Once we start reducing alpha, lambda reduces, and then we started getting more details and some texture in the results. And here, reduction of bias we reduce by measuring the standard deviation of in these uniform areas. So it is increasing. That means we are starting getting back the texture. So these are the results with reducing lambda further. And once lambda goes to 0.5, this is the maximum bias reduction we can get with this network assembly. So you can see that this image has a lot more detail compared to mean square error, and it has higher standard deviation. So alpha gives us like continuous control over how much bias reduction we can achieve. So this is the maximum bias reduction that can be achieved with this two network assembly. But we also have a generalization that if we increase the number of branches in the network, then this you can reduce bias further. So let's see actual results like on qualitative results on clinical examples. So this is noisy input, and this is the mean square error, so which looks very smooth. And then this is the proposed result with alpha 0.75. So we can see that a lot of details are coming back, and we got a lot of texture back. This is another slice of the same exam. As you can see that this feature, like this vessel, was completely lost in MSc, and we could recover it in our bias reducing loss function. This is orthogonal scan of the same exam. So this performance is consistent even in orthogonal planes. So this vessel was not visible in MSc, and we successfully recovered it. These are the lung images. So you can see that this is lung fissure, and it is completely lost in MSc, and we could recover it to some extent in bias reducing loss function. These features look very small to us, but for radiologists, these are very important, and they need to have every minute detail in the images to reliably diagnose the conditions. So yeah, these images show that the bias reducing loss function brings back the texture and detail compared to mean square error. So are we done? Then not really, because if we compare noise power spectrum, so this green is the target texture, what we want to achieve, and then black is the mean square error, which is skewed to the 0th frequency. And the magenta line is the noise power spectrum for bias reducing loss function. So you can see that we are recovering some high frequency content, but not completely. We are far, far away from green line. That's where so we don't have, we are not yet matching the shape of noise power spectrum. So that is the goal of texture matching GAN. How do we match the shape of noise power spectrum? So noise power spectrum is just mathematical representation or characterization of texture. So to match noise power spectrum in enhanced images, we propose to generate texture with the same distribution as the target texture. So GANs are the networks to achieve this, because everyone must be like knowing this. So I'll just keep over this part quickly. So generators are supposed to generate samples from the ground truth distribution, and discriminator is supposed to score the performance of generator. And after training in this assembly, in inference phase, generator are supposed to generate samples from ground truth distribution. So we can use generator to generate texture with the same distribution as target texture. And there are existing GAN-based method in city imaging. They retain texture to some extent. So what they do is their input is noisy or blurred city images. They use generator to enhance those city images, and then they input entire city images to the discriminator, and then discriminator gives the score, and then generator is trained to generate enhanced city images more similar to the ground truth city images. The problem with this architecture is that it could still introduce some artifacts because of hallucination, because discriminator doesn't concern itself with the actual content of city images. It just checks if the enhanced images looks like city images or not. So it could have some artifacts or hallucination or fake details. So that's not desirable. So our idea is to match the distribution of generated texture only to the target one. So, but the main question is, how do we separate texture from anatomy in the city images? Because as you have seen in those images, they are pretty embedded and we don't have separate scan for the texture and anatomy. So let's start with the problem formulation. This is our former model. So X is our true image and G of X is the deformation. So for example, in sharpening application, G of X could be blurring or low pass filter. And then W is additive noise. So Y is our observed image. Then our estimate is X hat, which has three components, and it is a function of Y, observed image. So the three components is the true image X, then B of X, which is the bias in the estimate, which is deterministic if we know X, and then delta of X is the noise in the estimate, which is X hat minus this conditional expectation of X hat. So this delta X is a random variable and it is a function of X. So existing algorithms like mean square error based algorithms, basically they try to eliminate this delta X completely, producing oversmooth results. So we propose to train our network to generate delta X with desired texture distribution. So it would be a valuable contribution to this X hat. But the problem here is we cannot observe this delta X directly. So what we propose is to observe the differences of noise in the estimate. So how do we do that? Again, we have the same ground truth image, and then we add two independent noise samples to the same ground truth image to produce two noisy inputs. And then we get two estimates from our network. So these y1 and y2 are conditionally independent and they follow the same distribution. And X hats also follow the same logic. And then we take the difference. So if we substitute the three terms as we discussed on previous slide, X and BX would be the same because our ground truth image is same. So they would get cancelled out. And then we'll just get delta X1 minus delta X2, which is the difference of noise in the estimates. So we assume that we have IID samples of the target texture and delta follows a distribution that is symmetric about 0. So, and then we propose to match the distribution of X hat minus X hat 2 to the distribution of this, the distribution of difference of true target texture samples. We have proved that if we match the difference, then delta X also follows the same IID same distribution as this target texture for a simple Gaussian case. And that theorem is inspirational, and but results show that this is also true practically. So let's see how we implement this. So again, we have the same ground truth image xk. we applied the deformation in the application, and then we add the important part is adding two independent samples of noise to the images, and then we pass them through our generator. These two boxes again share the same set of parameters, so these are Siamese network, and then we get two denoised estimates, x hat k1, x hat k2, and then we take the difference of these two samples. Then we also have true target or target texture, which is TK1 and TK2. We take the difference and it looks like this. And it forms the real input to the discriminator. Then note that the amplitude between the real texture and the texture, these images could be different. So to compensate that difference, we have this scaling factor gamma. This tunable, or we can set it manually. For these experiments, we set it, training sets it, and we didn't set it manually. So this is, so we scale this delta x1 and delta x2 by gamma, and then this is our generator output texture, which is a fake input to the discriminator. And then discriminator scores this fake texture by comparing it with the real texture and gives scores to the generator, and generator gets trained accordingly. And we also need to maintain proper details in the images. That's why we have another loss function for generator, which is bias reducing loss function introduced in the first part. So this assembly of taking a difference eliminates the hallucination part, because since we take the difference, the anatomy part gets removed because it's the same for the same ground truth image, and then what is remaining is just a noise. So even if discriminator introduces some fake details, it is embedded in the noise, so it is not recognized at the recognizable level. So this is the key part of the TMGAN. And once we train, we can use TMGAN generator to generate the results, enhance the images. These are the loss function. With the common literature, like we following the common literature, we use the binary cross entropy for discriminator. And for generator loss function, we have this term which is a discriminator score, and it is the loss for the texture part, and lambda controls the relative importance of this texture loss in the total loss function. And the second term is the bias reducing loss function to match the denoised image or deblurred image with the clean image. So here lambda, sigma, and alpha are the tuning parameters or hyperparameters in this algorithm. So this is a pseudocode to train TMGAN, which is very following the common literature in GAN. One key part is like we don't want discriminator to get too strong, so we update discriminator only if its loss function is greater than some threshold. This threshold is 0.2, so we update discriminator only if its loss function is 0.2. And for every generator update, we do multiple updates on discriminator to avoid mode collapse. TMGAN blending. So this is not the part of core algorithm, but this is necessary for practical implementation. So ideally, we need to tune alpha, lambda, and sigma to get the desired balance of texture and image detail. But the training process is quite time consuming. It is complex, and it could involve like a lot of combinations of these three parameters. So what we propose is the blending scheme in the inference phase. It can be used after we train for reasonable values of alpha, lambda, and sigma. So the blending is of TMGAN results and then bias reducing loss function. So this blending preserves the good amount of detail from Bayes reducing loss function and good texture from TMGAN, as we'll see in the images. So this is the experimental setup. Again, we take noise from water phantom. And since the noise in the input images is from water phantom, we also take texture samples from water phantom. And we compare our method with for denoiser we compare our method with WGAN VGG, which is Wasserstein GAN. It is a famous paper in CT imaging using GANs. And for sharpness, there is noise preserving sharpening filter, which was proposed by us to preserve noise texture while sharpening. So these are the hyperparameters. We can go over later if anyone has questions. So let's see if TMGAN is performing as expected or not. So this is the input. So these results I'm showing only on the noise images. So this input is the so in CT images there are different kinds of kernel to reconstruct images in the image domain. So to put it briefly, like these reconstruction control the frequency content of your images. For example, standard kernel is the most widely used kernel, which is just the filter back projection basic algorithm for CT reconstruction. Then there is bone kernels, which are like high resolution kernels, so they preserve more detail in the images. So this input image is reconstructed with bone plus kernel. And so this noise power spectrum looks like the orange curve. So you can see that this has like a lot of high frequency content. Now our target texture is the reconstruction with standard kernel, and it looks like this green line. Its NPS is the green line, so it has lower frequency content, and that's our target texture. And then the other three results are the TMGAN results with increasing lambda. So to recall, lambda is the weight of the texture loss term. So as we increase lambda, the weight of the texture loss increases. So we should get more and more texture. So you can see that in images with lambda 0, we get flat noise. Then with lambda 0.01, we started getting back texture, but it is not completely uniform or grain is not same as the target. And then lambda 0.04, we are very close to the target texture. And that's what we see in the noise power spectrum too. This black line is lambda equal to 0, and then magenta is 0.01, and then red line is the lambda 0.04. So as we got to 0.04, we are very close to the target texture in terms of noise power spectrum and even visually. But the noise standard deviation is reduced. So this is very close to what we decided as a goal in the beginning of this presentation. So let's see the PSNR, peak signal to noise ratio for these images or results. So this is the green is the PSNR of the input. Then the orange is the PSNR of the mean square error. So mean square error is optimized to maximize the PSNR. So it would give the maximum PSNR. That's guaranteed. But PSNR is not a good metric of image quality because it tends to give higher score to the smooth images. Then this Bayes reducing loss function gives slightly less PSNR, but as we saw, it gives more detail. Now, TMGAN preserves more texture. So it is interpreted as noise, and then it gives like very small PSNR value. So there is like almost 8 dB drop of PSNR, which might not be acceptable in clinical conditions. That's why we propose this TMGAN blending, and it gives like much higher PSNR with much better texture and detail. Wasserstein GAN VGG, which is benchmark from literature, it gives like PSNR somewhat between the TMGAN and TMGAN blended. These are the PSNR values and SSIM values. So SSIM is the structure fidelity metric. So it is the better metric for image quality. Um, we can see that Base-reducing loss function has the best SSIM, and TMGAN blended, which is we are proposing, it has like slightly less SSIM compared to batch racing loss function, but by showing the results, they produce much more pleasing texture than batch racing loss function. And as expected, PSNR is lower for these images. So these are the noise power spectrum for different denoisers. So our target texture is the green one, and the noisy input also has the similar noise power spectrum. So MS mean square error denoiser, it is the black line which is skewed towards the zero. As we saw, bias reducing loss function is slightly getting higher frequency component, and then WGAN VGG is still on the still gets like better higher frequency component, but it is still a lot more skewed to the DC frequency. So TMGAN is the best noise power spectrum in this image, and TMGAN blended is the second best noise power spectrum, and it also preserves a lot more higher frequencies than other methods. So the TMGAN blended matches noise power spectrum as much as possible, and it also preserves the detail and uniform texture. Um, so let's look at the images. So these are the clinical images, and then first is the noisy input, then second is the mean square error, then third is the bias reducing loss function. We can see a lot more detail in the bias reducing loss function. This is WGAN VGG. It brings back texture and detail, but if you look into zoom ins, this texture is not exactly uniform or pleasing or similar to the input images. This is TMGAN texture. So it looks a lot more like input texture, but this looks a lot more noisy compared to any of other images. And the last one is the TMGAN blended results, which blends like this column TMGAN with bias reducing loss function. So here we can see that the texture in this image is a lot more pleasing than this bias reducing loss function, and it also has preserved a lot more details compared to TMGAN. So that's why we propose TMGAN blended results for clinical applications. This is another slice of the exam. So here you can see that this area is very non-uniform, and even for such challenging areas, TMGAN blender produce pleasing texture, and it has preserved a lot more details compared to MSE or WGAN VGG or TMGAN. This is LCD exam, so it has low contrast, and we need to detect these features from exams. So performance on the LCD exams is also equally important because it's not always possible that patient would have a contrast. So this patient doesn't have a contrast in the vessel, so that's why this image has like lower dynamic range, and we have to identify such features. So you can see that texture is like very less in all of the methods. Bias reducing loss function has good amount of detail. TMGAN brings back almost a lot of texture, but this feature gets embedded in the noise, so which is not completely desirable. TMGAN blended, on the other hand, preserves nice, pleasing, uniform texture, and it also shows these features clearly in the images. So this method performs well on LCD images as well. This is another example of LCD image. So we have this feature bag with nice uniform texture. Um, This is a lung image. It might be slightly difficult to see. That in this image, there are like small pockets, like as we pointed by red arrow. These small air pockets are important for clinical observation. We can see that these pockets get almost blended in the background in the mean square error. They are very clearly visible in WGAN VGG or bias reducing loss function. For TMGAN, they get embedded in the noise. So, but TMGAN blended, they have good texture in the lung, and also these pockets are clearly visible. So this method works even on the different windows or lung image, different organ images. This is very challenging exam because the dynamic range is very, very low. So these are the important features clinicals would like to see. None of the images could recover it completely. Even TMGAN blended has struggled a bit, but it could recover those features to the extent possible, and it is better than any other images. Uh, let's see how TMGAN works on sharpening. So these are the noise pause spectrums for sharpening results. So here target texture and input again is embedded on this line, uh, the red and blue curve. Uh, so and then MFC sharpener sharpens the images, but it removes the noise. So the black curve is skewed to the DC frequency. And I have references for this NPSF method. So the the core of the NPSF gives like same noise as the input uh, in the output, and then it only sharpens the features. So it is also kind of texture preserving method, but it uses convolutional neural network, not GANs. And then blue line is the TMGAN method. So we see that all of these NPSF methods, they have the same noise power spectrum. So they perform similar in terms of texture, noise power spectrum. Let's see the actual images. So first is the blurred, noisy image. So then second is, this is the image of the brain. Then second is the mean square error. So we can see that it has sharpened the image well, but the noise in this area is gone. Then these are the NPSF, two variation of NPSF. And so this NPSF1 is what actually proposed, which matches the noise level of the input. And this NPSF2 is the where we match the noise level in the NPSF2 to the TMGAN for apple-to-apple comparison. So you can see that both of, and then last is the TMGAN results, and all of these images, they sharpen the features. Like for example, this feature, this is the ear structure. So this small feature gets sharpened in all of them, but the texture um, or like artifacts, these are the lines, cross lines you see here, those are actually aliasing artifacts because these images are reconstructed with high resolution kernel. Um, those are gone in TMGAN, but NPSF had to struggle with those artifacts, and even texture is more uniform in TMGAN compared to here. So TMGAN performs well even for the sharpening and compared to other methods. So in summary, so our goal was to denoise or sharpen city images while keeping the texture intact by reducing bias and keeping the shape of noise power spectrum intact. But the challenge is deep neural networks don't have explicit way to control both of these parameters, bias variance trade-off or noise power spectrum. So we proposed two algorithms to um, tweak these two features. So we propose bias reducing loss function to adjust the bias variance trade-off, and texture matching GAN to match the noise power spectrum. And these are our other publications on similar topics. Feel free to go through them and reach out if you have any questions. Any questions for today's talk?
Thanks for the excellent presentation, Madhuri. I will get started with the first query here. So, like the air pockets that we see on the CT scan images, so,
Mhm.
so, so there, these are, how do I put it? Yeah, these are the noisy kind of inputs that you need to prevent from going in at the end level, like preserving the detail and the nice texture that needs to go in. So, uh, so my query was like, uh, since you have kind of increased the texture and uh, the low contrast kind of uh, the the low and the high contrast clinical scan textures that have those particular details. So, did you also like experiment with different architectures here? Like since you have played with GAN and yeah, uh, so I was wondering about your next set of
So you mean images from other modalities like natural images or like that, or you mean
yeah
different?
in a sense yes, but my query was also focused towards a different architecture like the the VAEs and the other parts of stuff that
Mhm.
have come out recently. So like yeah.
Right. Yeah. So like we haven't, I haven't experimented with advanced models because this was like a year before when I graduated from PhD. So yeah, I haven't got chance to look at the advanced model, but uh, I think diffusion models would work better to preserve texture.
Mhm.
But the challenge in diffusion model is like inference time is quite long,
Mhm.
which is not uh, very good for like real-time CT scanners because we want to have like clinical images immediately for radiologists to analyze. So that's why like methods which have like less inference time, like for example CNNs or GANs, they are the best for CT scanners.
Oh, and plus, depending upon the size of the image too, since the CT scan resolution is high. So,
Right.
yeah,
Yeah.
yeah. And so you have also like played around with different organs, with the brain, with the lungs, and etc. So, did you find any sort of discrepancy between uh, like these set of organs and your algorithm, your TMGAN blended or your TMGAN, trying to find the difficulty in trying to yeah.
Um, so algorithm works pretty well, but like you might have noticed that the hyperparameters, they are quite
Mhm.
different between the sharpening or like sharpening we are basically apply for brain images and then other denoising. So tuning of hyperparameter is challenging as organs change and it's so we have to like calculate or determine hyperparameters in the beginning for different organs and then have them saved on the like for the real-time application. That is a challenge for different organs.
Hmm. Yeah, that's what I uh, like. Uh,
Mhm.
so uh, that might also become some sort of a like I'm cartoony texture or something like that. If like if your hyperparameters are not aligned
Mhm.
depending upon a particular or like is it also robust based on the different the outputs of different CT scan machines, so is it robust to that too, since like the paper and the color might be a bit different when the print is like
Right. Yeah, that is also sub. I mean, in city images, there are like different parameters. Like when they scan, like you might have noticed, like I've shown experimental side, they like voltage and amplitude. So it determines the noise level in the images. So we have tested these images in particular noise range. So if your input image is like drastically different from noise range, so model will still give some results, but like we have to like clinically analyze them if those are like perfect or not. So yeah, there is in medical images, there's lot more has to go into like generalizing your method.
No, yes,
Uh,
yes.
mhm.
So, are there any further work that is being done on this, or at Apple you're working on completely different things right now?
Right, at Apple, I'm working on completely different things.
Okay.
Yeah.
Okay.
Yeah.
Cool. If anybody else has any queries, then he or she might ask, or we may wrap up the call.
This is more like a general question, but like, how would you advise someone who's like trying to get into your field to like approach computer vision? Like, I just had a general query regarding this.
Computer vision, like this research is more on like image processing side, like enhancing imaging, denoising, and enhancing. So enhancing goes through much more scrutiny because radiologists look at these images directly. I haven't worked on computer vision like techniques like identifying some features in the images and then showing them to radiologists, but I assume that it would go through the same scrutiny. So like for medical images, there are like two parts. You as an engineer, like you work on your technique, but then your results get assessed not just like quantitatively, but by clinical experts for each and everything. So you have to be prepared for all of that end-to-end flow. And it's always better to work with the clinical companies, for example, G Healthcare or Siemens or other companies. So yeah, I think that's the advice. And there's a lot more in like for natural images, the range is just 0 to 255. For city images, the range is from 0 to 4,000. And then you can, like for lungs, we use like different range of values in the image. And then for liver, we use different range of values. So there is quite a domain knowledge to apply computer vision on these images. So one has to be familiar with those things.
Gotcha. Thank you so much.
Mhm.
Uh, just a last query here. So you have experimented with the special frequencies here. So in the frequency spectrum, there are many others that you could have also played around with. So is there a particular reason for fixating to these kind of frequencies?
Um, I mean, you mean about the noise power spectrum?
Yeah, the
So
the noise spectrum that has the, as you alluded to earlier in the presentation, uh, the the image that you showed regarding suppose the generated textures, and you're trying to denoise it based on like the input textures and the target textures that you had. So you kind of deal with the noisy inputs like on the spatial frequency parameters. So I was wondering about that.
so the choice of like frequencies we deal with and the noise power spectrum, it's mostly from like what clinical experts like.
Uh-huh.
So they are interested in those frequencies, and that's we got from. So they are familiar with the very traditional images, which are obtained with filter back projection, and the filter back projection has those frequencies or that kind of noise power spectrum. So we use that as a reference. So that is from like the clinical point of view. We didn't explore other noise power spectrum yet, but yeah, that is a good direction to check.
Yeah, thanks.
Mhm.
With that, I would like to say thank you for your excellent presentation and the Cohere for AI, and looking forward to see what you do next. And yeah, come again soon.
Yeah, thank you for inviting me, and it was nice experience. Thank you.
Bye. Take care.
Yeah, bye.